Here's an example problem using impulse and momentum. It's actually a version of a variation of a problem that we worked earlier with work and energy. In fact, we're going to have to use work and energy along with impulse momentum to solve this problem. You might remember this problem from earlier. We have a loop. We're going to try to make sure that the ball can actually completely go around the loop. And so before, we dropped the ball from a given height and just used work and energy. This time the ball is going to be starting from rest on the level surface here, and we're going to apply a force to it and again try to find the minimum force that's required for the ball to be able to make it through the loop. The force profile is defined here. We want to go from 0 up to the maximum value of the force linearly over 1 second. Hold that force for another second and then remove the force altogether. So the force is applied only over a 2-second interval. Now, before we can actually use impulse momentum, as I said, we're going to have to use work and energy. So this is a repeat of something we've done before. The ball is going to travel a circular path with a radius of 14¼ feet. And that's actually a helical path, but that third dimension, the pitch of the helix, is small compared to the other two. So approximating this as a planar path should be okay. And if we look at a free body diagram at the top of the loop and take the sum of the forces in the normal direction toward the center of curvature, we have the normal force between the ball and the track. We have the weight, both of those acting toward the center of curvature, and they add up to equal the mass times the acceleration in the normal direction. We can solve that for the normal force and put in our expressions for the normal acceleration, v squared over rho, the radius of curvature of the path, and the mass times acceleration due to gravity for the weight. Now, if we want to find the minimum speed to stay on the path, then we set this value equal to 0. So where we lose contact between the ball and the track, that's going to correspond to the minimum speed. And so solving for that, of course, the masses cancel out, and we come up with a velocity of 21.4 feet per second that we need to have at the top of the loop. And we can now find the velocity at the bottom of the loop by using work and energy. At the bottom of the loop, we're trying to find the velocity here, so we have a kinetic energy corresponding to that velocity. We can set the potential energy to 0 by calling that the datum. At the top of the loop, we have, again, kinetic energy based on the velocity we just calculated, and we also have the potential energy of the weight times the height. And we know what the height is, and we also know, again, what the velocity is at the top of the loop. So, applying our conservation of energy equation and plugging in all of our known values, the only unknown, as we said, is the velocity at the bottom of the loop, and we can solve for that, and it works out to just slightly under 48 feet per second. Now we can actually use impulse and momentum. And so the principle is this. We're only interested in linear motion here, and only in the x direction. So the initial mass times velocity is equal to the final mass times velocity, but we have to add the impulse, the sum of the impulses of any forces that are acting on the ball. And we only have one force, and it's acting in the x direction. So that middle term, the sum of all the impulses, is simply the one impulse, which is the area under the force time curve. And so here's the force time curve once again. And calculating the area, we have a triangular area and a rectangular area, add them together, and we get 3/2 times f with units of seconds. So when we put in the value of the force in pounds, then the impulse is going to have the units of pound seconds. And so applying our equation here, we know that the initial momentum is 0 because we start from rest. The sum of all the impulses is the 3/2 f times s, and the final momentum is the mass times the velocity, and we know the velocity that we need to reach is about 48 feet per second. So we can solve that for the value of f, and it turns out to be slightly less than 40 pounds. Now, before we go to the SolidWorks simulation, the way we're going to apply the force, there are several ways to do it, but the way we're going to do it is simply with a single force. We set its value to 0 at time equals 0. Then edit that to have a value of 40 pounds at time equals 1 second. Also have a value of 40 pounds at time equals 2 seconds, and at that point we turn the force off. You notice the blue bar between the time 0 and 1 second. What that indicates is that the force will be increasing linearly between those two times. Okay. So here's the simulation, and we're running this with a maximum force of 40 pounds to start with. So according to our calculations, we should be able to make it around the loop with not much to spare, but makes it through just fine. And if we want to look at the graph here of the velocity of the ball versus time, you can see at this point right here, this is at time equals 2 seconds. This is where the force is actually removed, and so there's a small area of constant speed before it hits the loop. And of course, when we get to the minimum speed right here, that's at the top of the loop, and you can see we're at about 22 feet per second, so very close to the calculation that we made. If we drop the force much at all, then our velocity is going to drop below that necessary to keep the ball engaged with the loop. And in fact, let's go down to a very low force here of 25 pounds. So drop from 40 down to 25 pounds. And you can see in this case, the force is not enough to get the velocity high enough to even be able to make it halfway up the loop. If we increase that up to 35 pounds, we'll see if our calculations, how accurate they are, because this should be just not quite enough to get there, and we can see, yeah, that is the case. Don't quite make it there. Now, again, how accurate are our calculations? We calculated a value between 39 and 40 pounds. So our calculation says 39 pounds shouldn't work. Let's see what happens. And in this case, we actually do make it around the loop. But it's kind of interesting if we take a look at a different view of that. You may have noticed what happened here, but we'll play it from here. And you'll see when the ball comes around that it actually does lose contact with the loop, but has enough momentum in this direction that it actually hits back onto the path and does make it around the loop completely.